MODO. Morsels.
The audience has spoken, and he would like to know more about Quaternions, so this morsel will be a little different. MODO has channel modifiers that create, decompose and manipulate these mystical mathematical objects. So what are they, and why would you want to use them? The executive summary is that in the CG world they are used for rotations. A Quaternion spherical linear interpolation, aka slurp, is much better than naive interpolation of matrices and Euler angles. Composition of Quaternions is cheaper to calculate than composition of matrices, but vector transformation by Quaternions is somewhat more expensive. So, if that's all you wanted to know, you can stop watching now. Please pay at the kiosk as you leave the auditorium. The invention, or discovery depending on your philosophy of maths, of Quaternions is attributed to Sir William Rowan Hamilton. Of course, Carl Friedrich Gauss probably got there first, but he didn't publish anything, so didn't get the credit. Not that he needs any more recognition. Hamilton was looking for a 3D analogue of complex numbers, but nothing seemed to work. His eureka thought was to add an extra dimension, and so the 4D Quaternions were born. Quaternions are a generalization of complex numbers, which you may recall are composite numbers with a real part and an imaginary part. A complex number is written x plus yi. I is the imaginary unit and I squared equals -1. Complex numbers are really useful mathematical tools which crop up everywhere. Because they can represent quantities with magnitude and a phase or angle, they are used a lot in the physics of waves, including, for example, AC electricity. Quaternions are so-called hypercomplex numbers and go one step further. The rule for the imaginary components is an extension of the rule for the complex numbers, such that I squared equals j squared equals k squared equals ijk equals -1. Quaternions and complex numbers can be manipulated using all the familiar arithmetic operations, for example, addition, subtraction, multiplication and division. Just follow the rules and crank the handle. It's worth noting that Quaternions are not commutative. That is, A times B and B times A are not necessarily the same thing. You are probably used to describing rotations with so-called Euler angles, or what you might call pitch, yaw and roll in aviation terms. Alternatively, you might have seen a matrix. These representations have some undesirable features. It is hard work to combine rotations using Euler angles. They also suffer the dreaded gimbal lock problem. Matrices are wasteful and over-specified in that they require 9 numbers, 3 orthogonal vectors, to represent a rotation, whereas a Quaternion only requires 4 numbers. Matrices can suffer from numerical problems, so that even combinations of pure rotations can end up decaying into non-rotations, and fixing this is hard. Quaternions can be trivially renormalized to make them into pure rotations. So what does a rotation look like as a Quaternion? There is a special class of unit Quaternions, ones whose magnitude is 1, which look like this, where theta is half the rotation angle and xyz is a normalized vector, the axis about which to rotate. Exercise for the viewer. Prove that Q is indeed a unit Quaternion. To rotate a point ABC around an axis xyz with a Quaternion, you calculate Q times IA plus JB plus KC times Q star, where Q star is the conjugate of Q, that is the same Quaternion but with the imaginary parts negated. Most of MODO's tools work with Euler angles at the UI level, and these are converted to matrices internally. If you want to use Quaternions instead, then MODO provides a set of channel modifiers to help you, and these fall into three categories. There are modifiers that create Quaternions from other representations, manipulate those Quaternions, or convert Quaternions to other representations. When creating Quaternions, we can use raw numbers, but these will not necessarily be rotations, remember the rule given previously. Or we can convert from Euler angles, matrices, or axis angle representation into Quaternions. Once we have a Quaternion in our hands, we can do things to it. We can add, subtract, multiply and divide. Note that multiply is really the only one we will likely need, as when we multiply two rotation Quaternions together, we get the concatenation of the two rotations. We can normalize Quaternions, i.e. divide by the magnitude to obtain a unit Quaternion, and we can create a conjugate, which for rotations is also the inverse. The next two operations are the most important. Vector Quaternion multiply applies the rotation to the vector. This is how we transform points using Quaternions. It is the equivalent of the matrix vector multiply operation, but it is a more expensive operation than the matrix approach. SLIRP, short for spherical linear interpolation, can be used to step from one Quaternion to another using a blend factor from 0 to 1. Matrix blend does the identical operation for rotation matrices, but is more expensive. SLIRP moves along a great circle, i.e. the shortest distance between two positions on the surface of a sphere. The linear part means that the steps are even. This makes it ideal as the basis for animations. Finally, we can convert our Quaternions back into Euler angles, matrices, or axis angle representation. Or we can extract the components of the Quaternion. Let's look at some examples of Quaternions in action. In this example, we create two Quaternions from an axis angle form, then compose them using multiply, and finally convert to a matrix to feed into the mesh's rotation channel. In the second example, rather than composing the transformations, we blend using a SLIRP to get the intermediate rotations. In this final scene, we see the difference between a SLIRP using Quaternions and a naive interpolation of Euler angles. Notice how the SLIRP is evenly spaced, whereas the naive approach is uneven and takes a rather bizarre route. If you interpolate the matrices naively, you get even worse results. Thankfully, in the places that matter, MODO does the right thing. If you want to stay in matrix land, then the matrix blend operation will perform the same SLIRP interpolation. That's probably more than you'll ever need to know about Quaternions. If you want a more mathematical treatment, I can heartily recommend checking out 3 Blue 1 Brown's videos. I suspect that for most purposes in MODO you will be fine using Euler angles and matrices, but the Quaternions are there should the need arise.
Morsels.